Okay, so we're going to start with chapter 3 today. And in chapter 3, we'll be dealing with this area, very important fundamental area in chemistry, known as stoichiometry. And basically, stoichiometry is that area in chemistry which deals with quantitative relationships between substances involved in a chemical reaction. All right, so that's basically what stoichiometry is all about. But before we get into the actual meat of stoichiometry, we have to define some terms. And again, these terms you should have met before in your introductory or high school chemistry. So this will be a bit of a review. So let me go to full screen mode here. So the first definition here is that of molecular mass. And that, by definition, is the sum of the atomic masses of the atoms represented in a molecular formula, right? And we all know how to calculate that. Is all based on the formula. So for example, in the case of water, in fact, let me get out of this here and go to this here. So let me make sure this is working. Okay, so in the case of water, for which the formula is H2O, the molecular mass will be equal to 2 times the molar mass or atomic mass of water, which is 1.008 AMU, plus for oxygen, if you look it up, it's 16.00 AMU. Oops, AMU. And when you work that out, that should give you 18.02 AMU. All right, so basically you add the atomic masses according to the formula. Because you have a 2 here for the hydrogen, you multiply the atomic mass of hydrogen by 2. In the case of oxygen, there's a 1 here, so you basically leave that alone, and you add it up, and you end up with the result, which would be the molecular mass, all right? Now, as stated here, going back to this slide, the term molecular mass applies specifically for molecules, right? So you would not apply molecular mass to anything other than molecules. Now, in the case of ionic compounds, which of course don't exist as molecules, then there's an alternative term that we use, and we apply it specifically for the formula unit. If you remember, we talked about the formula unit in the previous chapter for an ionic compound, which is basically the empirical formula for the particular ionic compound. And therefore, the formula mass is the sum of the atomic masses of the atoms or ions present in a formula unit. All right, so for example, let me go back to this again. So for example, in the case of sodium chloride, NaCl, that's the formula for sodium chloride. So therefore, the formula mass in this case, because we cannot use molecular mass, that will be equal to the molar mass, or the atomic mass, I should say, of sodium, which is 22.99 AMU. And in the case of chlorine, it is 34, if I remember correctly, 34.45 AMU. And we add them up. So 22.99 plus 35.45. So the answer becomes 58.44. This is equal to 58.44 AMU. All right? So that's basically the difference between the formula mass for an ionic compound and the molecular mass for a molecular compound. All right? Okay, so let me go back to the PowerPoint again. So, excuse me. Let me scroll to the next slide. Okay, so this is an example. It says calculate the formula mass for ammonium sulfate. So in the case of ammonium sulfate, of course, you have to figure out what the formula is. And based on what we completed in chapter 2, by now you should all be experts in writing down or determining the formula for a compound, ionic compound. In the case of ammonium sulfate, let me change this color here to black. I prefer that. Okay, so the formula for ammonium sulfate would be NH4 2SO4, right? So therefore, what we'd have to do is go to the periodic table, and we have to look up the atomic mass of the respective elements. So I'm going to pull up the periodic table on another computer here. So I can, okay, tables chemistry, download. Okay, so I got my periodic table in front of me. So in the case of nitrogen, um, the molar mass or the atomic mass of nitrogen is 14.01 AMU plus 4 times the molar mass of hydrogen, which is 1.008 AMU. And then that sum you have to multiply by 2. So I'm going to put it in square parentheses here and multiply by 2 because of this 2 right here. And then to that, I'm going to add the atomic mass of sulfur, which is 32.06 AMU, plus 4 times the atomic mass of oxygen, which is 16.00 AMU. All right. So let me do the number crunching here. 14.01 plus 4 times 1.008 equals that. Then multiply by 2 equals that. Then I add to that 32.06. And then I add to that 4 times 16. And the answer I got here, and we'd have to round off the answer to 2 decimal places. So the answer I got here is 132.14 AMU. Let me do a quick check just to make sure that I'm actually telling you guys the right thing. Okay, what's going on with this? Okay, so, okay, what's going on here? All right, so yep, that's correct. Okay, good. So that's basically how you'd calculate the formula mass of ammonium sulfate. All right. So it's pretty straightforward. All right. So let's move on now to a discussion of some other terms that you should be already familiar with. Again, we're going to go through this rather quickly. So we're going to talk about the mole concept and the related Avogadro's number. All right. So let's talk about what we mean by the term mole. And as you can see here, by definition, a mole is an amount of substance that contains as many elementary entities as there are atoms in exactly 12 grams of the carbon-12 isotope. So as you can see here, this definition here is based on what happens or what is present in exactly 12 grams of carbon-12, right? So by definition, 12 grams of carbon-12 would be equal to 1 mole. And it turns out that the number of carbon atoms present in 12 grams of carbon-12 is a very large number. And that number is Avogadro's number, which is given right here. It is 6.02 times 10 to the 23 per mole, or mole to the minus 1, right? So basically, the relationship between the mole and Avogadro's number is 1 mole, right, of any substance contains Avogadro's number of particles. And those particles could be atoms, could be molecules, it could be ions. It all depends on what we're referring to. All right. So 1 mole is equal to 6.02 times 10 to the 23 things. And in actual fact, as stated here, the mole concept here applies not only to atoms, but can literally be applied to anything, any item. So you can have 1 mole of oranges, 1 mole of human beings, 1 mole of chicken. I mean, it can apply to literally anything. But of course, in chemistry, since we are concerned with atoms and molecules and so on, that is where we typically apply this whole mole concept, all right? And just to give an idea as to what we're talking about here, if you were to have 1 mole of oranges, that would weigh about as much as the mass of the Earth, all right? So that gives an idea as to how large a number 1 mole is, all right? One point being made here is that when it comes to abbreviation, we do not use uppercase M or lowercase m. And actual fact, come to think of it, this is not technically speaking true, because I've actually seen in some textbooks where they use lowercase m, but instead of writing it in the ordinary print or font, it is normally done in italics. All right, but and even that is a bit what's the word I'm looking for? Ambiguous, because I've also seen them use lowercase m in italics for another um, unit of measurement, which I won't get into. But anyway, typically what we use for mole in terms of abbreviation is MOL, right? So MOL would be the abbreviation that we would use for the mole unit, all right? Okay, so just to show you the relationship between mole and the number of atoms and the mass um, of the substances involved, let's look at this reaction here. Very simple reaction, the reaction between carbon and oxygen to form carbon dioxide, all right? So, as you can see, there's a 1:1:1 ratio between the number of carbon atoms, the number of oxygen molecules, and the number of carbon dioxide molecules. So therefore, one carbon atom will react with one oxygen molecule to form one carbon dioxide molecule. So you can imagine if we have a dozen carbon atoms here, right? That means that it will require a dozen oxygen molecules, and therefore what would be produced would be a dozen carbon dioxide molecules, all right? So if we extend it to 1 mole, now remember 1 mole contains a huge number, Avogadro's number, 6.02 times 10 to the 23 particles. In this case, we're talking about 1 mole of carbon atoms, so that would be the number of carbon atoms, and therefore based on the 1:1 ratio between the carbon, the oxygen, and the carbon dioxide molecules, then you'd expect that the number of oxygen molecules required and the number of carbon dioxide molecules produced will be the same. Now, it turns out that the masses would be different for each of these, right? It turns out that the mass of 1 mole of carbon atoms is 12.011 grams. For 1 mole of oxygen molecules, it's 31.9988 grams. And in the case of 1 mole of carbon dioxide molecule, that mass would be equal to 44.010 grams, all right? So the point that is being made here is that even though the number of moles of each of these substances, the reactants and products, are the same in each case, that does not necessarily mean that the masses would be the same, right? It turns out that the mass of 1 mole of carbon would be different compared to the mass of 1 mole of oxygen, which would be different compared to the mass of 1 mole of carbon dioxide, all right? So this brings us now to, before we get to the molar mass concept, this is just demonstrating different substances, 1 mole of each, right? So what we have here is 1 mole of sulfur right here, this yellow substance here, 1 mole of copper, 1 mole of mercury, and in this balloon here, we have 1 mole of helium. And the question being asked, the question being asked here is how many atoms of helium are present? And they're asking the same thing for sulfur, for copper, and for oxygen. How many atoms are present? Well, because it's 1 mole of each of them, the answer would be Avogadro's number in each case, right? 6.02 times 10 to the 23 atoms of helium is present in 1 mole of helium. The same is true for sulfur, the same is true for copper, and the same is true for mercury, all right? So that's basically the answer to these questions, all right? So again, you need to remember the relationship between the mole unit and the number of atoms present in a particular element, right? 1 mole of any substance, or I should say any element, will contain Avogadro's number of that element. And as we just learned in the previous slide, 1 mole of a substance does not translate, well, if you compare two substances, 1 mole of one substance will not necessarily have the same mass as 1 mole of another substance. So that brings us now to the concept of the molar mass, right? So we just talked about the fact that basically different substances may have different masses for 1 mole in each case, right? So that brings us now to this definition, molar mass. By definition, the molar mass of a substance is a mass, usually expressed in grams, of 1 mole of a substance, right? And it turns out that the molar mass is actually numerically equal to the atomic mass for elements, molecular mass for molecular compounds, and formula mass for ionic compounds. So numerically speaking, for any substance, the molar mass is the same as the atomic mass or the molecular mass or the formula mass, depending on the type of compound we're talking about. However, you need to recognize that the units of molar mass are different from the units of atomic mass, molecular mass, or formula mass. The units of atomic mass, molecular mass, or formula mass is AMU, all right, atomic mass unit, while the units of molar mass is, as stated here, grams per mole, right? So please note that even though the molar mass is numerically equal to the atomic mass, or the molecular mass, or the formula mass, the units are different. The units of molar mass is grams per mole, while the units of atomic mass, molecular mass, or formula mass will be AMU. All right, so just to give you some examples to help you understand the distinction between the units as regards to molar mass versus atomic mass, formula mass, and molecular mass. Let's take sodium. So for sodium, the atomic mass of sodium is 22.99 AMU, right? That's the atomic mass. But the molar mass of sodium is 22.99 grams per mole, all right? Numerically, they're the same, but the units are different. If you look at the molecule carbon dioxide, the molecular mass is 44.01 AMU, but the molar mass of carbon dioxide is 44.01 grams per mole. All right, and I think I have one more example here. This is an example of an ionic compound. In this case here, the formula mass of potassium chloride is 74.56 AMU, but the molar mass of potassium chloride is 74.56 grams per mole. So as you can see, in each of these cases, numerically speaking, the molar mass is the same as the atomic mass in the case of sodium, the molecular mass in the case of carbon dioxide, and the formula mass in the case of potassium chloride. Numerically, they're the same, but the molar mass units will be different from the units over here on this side, because the molar mass units are expressed in grams per mole, while the atomic mass or molecular mass or formula mass will be expressed in AMU units, all right? Okay, so with that said, let's conclude what we have talked about earlier in terms of the relationship between the mole unit, the number of particles, and the molar mass, right? So basically, this is an equation here which ties together the different concepts that we have learned so far, right? For 1 mole of a substance, the number, in this case, the substance is sodium, right? But this applies to pretty much anything else. So let's talk about sodium. 1 mole of sodium contains this number of sodium atoms, all right? 6.02 times 10 to the 23 sodium atoms. And the mass of 1 mole of sodium is also equal to 22.99 grams, all right? So we have two equalities here. We have a relationship between sodium and sodium atoms. We have a relationship between sodium atoms and the molar mass expressed in grams. But we also have the relationship, come to think of it, between the sodium mass and the moles of sodium. So we can write down conversion factors representing any two of these involved in this relationship. So we can write down this, for example, which shows you the relationship between the moles of sodium and the mass of sodium, or we can flip it to get this, or we can write this relationship down. 1 mole of sodium is equal to 6.02 times 10 to the 23 sodium atoms. Or we can write down the relationship, which is not written here, but we can write down a conversion factor, which represents the relationship between Avogadro's number of sodium atoms and the molar mass of sodium, all right? So those are the different types of relationships we can establish based on this relationship right here. We can write down different conversion factors based on what we have up top here, right? And of course, the relationship that we're going to use in any problem-solving exercise is dependent on, what is given in the question and what the question is asked for. And we're going to see some examples of this shortly, all right? So as stated here, when you're doing these problems, preliminary and follow-up calculations may be needed. We're going to see some examples of this shortly, all right? So the last thing I'm going to talk about in this series of videos or in this video here, I should say, this series of slides, is how do we interpret the formulas with respect to the number of atoms present per molecule or formula unit. So we're going to look at this example here. So let's say we have a compound, we're given this formula, C3H8O3, right? How do we interpret the actual number of atoms present per mole of this substance? So basically, all we have to do is look at the subscripts of the different elements represented here in the formula. And therefore, we can conclude that for every 1 mole of this substance, there are 3 moles of carbon atom because of the subscript here, 3 for carbon. There are 8 moles of hydrogen atoms because of the 8 here for the hydrogen. And there are 3 moles of oxygen atoms, right? So based on the formula alone, we can establish the mole relationships between the atoms that are present that make up the particular molecule and the molecule itself. And we can also apply that to formula units when it comes to ionic compounds. In this case here, we're working with 1 mole of ammonium sulfate, right? Now, in this case here, if we have 1 mole of ammonium sulfate formula units, based on the formula, we can conclude that for every 1 mole of ammonium sulfate, there are 2 moles of ammonium ions. And we can actually break this down further to separate the nitrogen from the hydrogens. So we can conclude that there are 2 moles of nitrogen atoms and 8 moles of hydrogen atoms, all right? And then for the sulfur, or for the sulfate, for every 1 mole of ammonium sulfate, there's 1 mole of sulfate ions, right? And we can break this down further to separate the sulfur from the oxygens. Whoops, sorry. So therefore, 1 mole of sulfur would be present for every 1 mole of sulfate, and 4 moles of oxygen would be present for 1 mole of the same sulfate, all right? Okay, so we're going to stop here for this video, and the next video we're going to go directly into some examples right here, all right? Okay, until next time.